Welcome to Statics and Structures for Construction Management. This is a class about how structures work. We want to consider the critical parts of structures, and we want to develop the techniques needed to analyze and understand structures. One of the first parts of this class is to develop an awareness of structural configurations. This slide shows a Volvo sign, but as we look at it, there is much more to it. The sign is raised above the building roof. In order to support the weight, there is a matrix of triangles fastened together to make a rigid structure. Furthermore, the structure needs to withstand the weight of the sign as well as the wind blades, while still allowing much of the wind to pass through it. For this class, I would like you to start seeing structures. In a sense, this is a process of training your eye to be able to see structural configurations. Even in this fairly bland photo of a canopy over a doorway, we see that the base of the canopy is fixed to the wall, and we see a cable or rod that supports the front end of the canopy. In this photo, there is a much more complicated structural configuration. This is the underside of an ocean pier at Topsail Beach, North Carolina. The decking boards at the top. These are supported by beams running parallel to the length of the pier, which in turn are supported by pilings. Pilings support this entire road, but they are braced by the diagonal braces running from the pile top to the pilings. But before we go any further, let's ask, why should you study statics, and what should you expect to get out of the class? One thing that you want to understand what to do is to understand the basic mechanics of loads and how these loads are resisted by structural components. With this knowledge, we have a better ability to contribute to and to manage projects. This also provides a better understanding of the properties of construction materials. Safety is another important consideration, where knowledge of statics can be beneficial. So, as we look at structures, we want to consider what stresses are present and how they impact the design and the choice of structural materials. A lot of statics of structures is solving problems. This brings us back to algebra, gravity, and trigonometry. We need to use these tools to evaluate structures. We also need to recognize that the process of solving problems quantitatively and the answers that we get are extremely useful for understanding statics. It's quite different to look at a structure and make some qualitative observations compared to our fully analyzing the structure using the quantitative tools to really understand it. So, what are the reasons for studying statics? One, because there's more segmentation and cost control in different projects. Many subcontractors, some of whom may not communicate with each other. Another thing is, number two, it gives us a place at the table. We can now contribute to discussions about building the building structure itself. Three, safety is an important consideration. Knowledge of statics calculates to both the safety of the building and its final completion and the safety of hazardous being. Fourth, reliability. The more we understand about statics and structures, the better imagery second. Fifth, additions and retrofit the older structures. Often nowadays we use the revolving loan to the old building, the older buildings, and having those more complexity and understanding what we can do and what we can't do. And six, living in different countries, states, and regions. Different rules across different building codes that can apply, and the more you know about styles and structure, it's a mechanism based on we will be doing problems, lots of problems, but we also want to be able to interpret results. And it's important to consider how you organize your answers so that you or someone else can go back and return what you did. In addition to solving problems, we can appreciate how structures have stood for centuries in our design. This is the fourth Rivertown South Edinburgh Scotland, completed in 1890. The Brooklyn Bridge was completed in 1883. The Norwegian Stone Church in Headwater dates back to the 13th century. And we have all seen photographs of the Roman. We also see structures that have gigantic inside. The Apache Bridge in Japan has the longest span on a suspension bridge, 6,532 feet. This photo shows the Astoria Edward Bridge at the mouth of the Columbia River and the border between Oregon and Washington. Another interesting structure is the enclosure, which is being built to enclose the wreckage of the Chernobyl nuclear power disaster. However, we also see many cases where structures fail on collapse. Hurricanes, tornadoes, and earthquakes are very significant problems for structural design. Which shows houses we remembered the 35W bridge collapse on August 1st, 2007. This disaster was attributable to undersized vessel planes. For example, some of the disaster Tony picture some of the bridge in the water. The failures of the Tacoma Valley Bridge on December 1940 and the Toll Bridge on December 28, 1879 are examples where the structure was not properly designed for the elements. Both of these bridges failed during heavy rains. Even the Sable Bridge in Minneapolis had to be closed and then repaired due to some issues with design and defects. In this case, migration of support cables causing vacuum plates to fail. Now, let's go back to geometry and here we have a right triangle. We have three primary trig functions to remember. One, the sine of theta is equal to the opposite of the hypotenuse. Two, cosine of theta is equal to the adjacent perimeter and the tangent of theta is equal to the opposite of the adjacent. It is important to learn these functions because we will use them over and over again. One other relationship that is useful to remember is that if we have two parallel lines and a third line which intersects each other, the opposing angles are equal, as shown in this diagram. Now, let's look at an example problem. Here we have a force, perhaps K1, pulling at this screw line. The force is 200 pounds and it is pulling at an angle of 60 degrees to the horizontal surface of the board. So, what is the vertical component? Or, in other words, how much of this force is directly vertical to the plane of thought? Now, this force is a vector with these characteristics: 1, magnitude, impact or range; 2, direction; 3, sense, where the sense is considered to be positive if it is directed upwards and towards the right, and negative if it is directed downwards or towards the left. And 4, the point of application, in this case it's the screw. We can separate this force into vertical and horizontal components. Here we construct a right triangle having vertical and horizontal lines. Given that the angle is 60 degrees to horizontal, the trigonometric relationship to solve this problem is sine of 60 is equal to y over 200. Solving for y, sine of 2. Similarly, we can determine the horizontal component by using the cosine. Here the cosine of 60 is equal to x over 200 pounds. And solving for x, we get an answer of 100. So, if you have two forces, one horizontal and one vertical, we can determine the resultant of these forces, the resultant being the combined effect of these forces. For this class, it is also important to understand how the structural system works. We need to recognize the different structural elements, and we need to determine the loads that will be applied to the structure. There are a number of classifications of loads. We have static loads, such as gravity, and there are dynamic loads, such as wind and earthquakes. Furthermore, some of the loads are permanent or dead loads, the weight of the delivery materials, while other loads are called live loads because they can move and change. We also need to be aware of how loads are transferred through the structure to the ground. This is called load tracing, as shown in this diagram. Another concept that is important to statics is that we are dealing with objects that are at rest, therefore the objects are in equilibrium, and the forces in each direction must be balanced. As a final note, a discussion of structures means to address structural materials. No properties is included metals such as steel and aluminum, concrete such as reinforced concrete, pre-stressed concrete, and wood.